Welcome back to Huawei Routing and Switching Elite Training for HCIE. Today topic we are going to discuss on other technologies. Let's start our part 3.
Now after the traffic policing, alright, now we are going to look into traffic shaping. Now traffic shaping and traffic policing are very similar. Okay, let's look into the difference between shaping and policing. Now first point here, when packets are sent at high speed, traffic shaping cache the packet. Now the cache is the difference over here, because in policing anything that is exceed the CRR rate will be discarded, but here we are going to do a cache in the buffer and then evenly send this cache packet based on the token bucket. So typically we are using it in the egress, alright, egress interface. Now let's look into this diagram. I have a packet that coming in, so they are going to do a classification and place them into the queue. Now some of the packet will not subject to the shaping, so it will immediately go out. Okay, example over here will be your routing protocol. Now assuming that those queue that do subject to the shaping will be placed into the queue and they are going to subject to shaping. So again, we also have the CIR and we also have the CBS. Now assuming that now in your interface you do not have enough bandwidth because that your B is more than your CIR. Now typically if let's say you are under the policing, if you have this B more than your TC, it will get dropped. But under the shaping, if it's B more than the TC, it will get into the buffer, or in this case a cache. So here is our cache. So packet exceeding the rate will be cache. Alright, it will go into your buffer queue. So when there is enough bandwidth, then this type packet will be queued to send out. But again, if let's say the queue is also full, then it get discarded. Okay, so the only difference between the policing and the shaping is basically this queue. Now the purpose of over here is that if let's say you have a traffic that you are going up, so let's say now this is your limit. Okay, you are going up, you hit the limit, it will actually come down, and then you go up, you hit the limit, it come down. So this is where you have policing. Now if let's say now you also have a limit that is based on your CIR, but this time is a shaping, what will happen over here is it will hit into the limit, then it will get constant as possible. Why? Because anything that is actually hitting over here, some of the packet will be cache. Alright, so the problem over here that this portion here is cache. Okay, rather than the drop as in policing, it will cache into your queue or into your buffer, and it will release it when you have certain spare capacity. So this is where when we want to deploy the shaping, it's always on the egress rather than in the ingress. Okay, now let's look into how we can configure the shaping. So since the shaping is on the egress, I'm going to apply it on the serial 100. Okay, so the command for me to do that, firstly let's jump into the serial 100. We use a QoS GTS. GTS stands for generic or general traffic shaping. Okay, then we are going to use our CIR. And if let's say the policing over here is 8 kilobit, so we also need to match the value as 8 and then specify my CBS as 1005. That's all you require for you to configure your shaping. Now please remember that we also can use a queue based traffic shaping. I'll show you later on how you can do that, but this is a single command for you to configure the generic or general traffic shaping. Now after we look into the shaping and policing, let's look into the congestion management now. Now what's the meaning of congestion management? So basically when you have a congestion, okay, when the packet that is reaching into my ingress interface and want to go out to the interface. So that is where the congestions occur. Let's say now you have 1 gigabit per second. And now when you go out, you only have 100 megabit per second. So you can see that the gigabit, 1 gigabit and 100 megabit. So if you are reaching to me faster, you are actually 10 times faster than you are allowed to go out. So what will happen over here is congestion. Alright, so this topic we are going to look into how you can manage these congestions and how to solve the issue. So to solve the congestions, we have to use a congestions management technology. This is what we are looking into now. So congestions management determines the sequence in which packets are forwarded according to the scheduling. So the queue scheduling that we are going to learn here, we have a different flavor. So first we have the first in first out or FIFO. We have round robin. Okay. We have the weighted round robin. We have the priority queuing, custom queuing, and weighted fair queuing. So we are going to look at all this queuing one by one. But let's look into this particular model to understand how this queue is being implemented. Now when all the packets start to come into my input interface, the first thing that the software is going to check, or the VRP is going to check, is that do I have a congestions or do I have no congestions? If I do not have a congestions, then straight away you'll go into your hardware queue. Okay, and is the hardware queue is full? No, that means that there's no congestions. Now you are actually going queue to queue out. All right, that's very simple. That is only if, let's say, there's no congestions. Now assume excuse me, assuming that now the congestions it actually occur. Okay, first is that there is a software queue here that check whether it's empty or not. So if it's not empty, then you are going to queue based on the software. Alright, so if let's say the queue is empty, then it will check whether your hardware queue is empty. Now most likely when you are coming in, when your software queue is not empty, then you will go into queue into the software, and the software then will have the queuing. Over here it can be FIFO or it can be round robin. So all this method will be implemented under the software queue system. Okay, so this is where we are going to look into all this one by one. Now the first congestions management over here is called first in first out or FIFO. Now FIFO, in effect, there is no quality guarantee, okay, and is subject to tail drop. Now the tail drop basically means that when the FIFO queue is full, those packet that is coming in later that join the queue, this packet will get dropped. Okay, that is what we call the tail drop. Now let's look into how the packet arrive. Now assuming that now I have this packet arriving, all right, as you can see that the packet are going to queue one by one inside the buffer, and once the buffer is actually full, it will subject to tail drop. And when you are the first who come in, you are the first who go out. Okay, that is in sequence. But over here, they do not have any priority. So basically means that even though they have a packet that is very urgent, it still queue behind the non-urgent and the second urgent priority. So all this red color that is under the priority that is urgent, if you are using a FIFO queue, it really doesn't take effect of your priority. So if you are using a FIFO and you have a classification, the classification basically is useless. The second congestions management will be round robin or RR. Okay, so RR perform scheduling through the pooling. So here we have a schedule, so that means that it is time based. So during the round robin scheduling, if the current queue has packet, the packet or the schedule will take the packet away from the queue. So for example, you can see that yellow on queue number 1, yellow will be queue here. Then once the yellow queue already taken away, there is no more queue behind here, then it go into the next queue, so which is the green color. So once you finish the green, it will go into the red color. So it's actually based on the sequence of round robin. What happens if let's say there is no packet? Okay, so if let's say there isn't have any packet on that particular queue, so the scheduler will skip over it without waiting the scheduled packet in the next queue. So assuming that there is no queue gray color on queue number 4, it will skip and then it will jump into queue number 6. Now later, if let's say they do have a packet coming in as a gray color in the queue number 4, you have to wait. So I have to finish all my queue, go back into queue number 1, and then it takes turns. So which basically means that this particular queue have to wait on its turn, and there is no such thing called wait. Alright, they don't consider any wait over here. So to improve this, we have what we call the weighted round robin. It's an extension of the round robin. Now compared to round robin, each of the queue have a weight. Alright, so you can see that queue A have a weight of 3, queue B have a weight of 2, and queue C have a weight of 1. So with the weighted round robin, packet in all the queue are scheduling in turns, very similar to RR. But the WRR schedule packet based on its weight. So which means that if you have a higher weight, you will have the higher chance to go out. Okay, then this is yellow, then this is the green color. Okay, and then it actually take turn. Now compared to the round robin, so now I have a weight on the queue. Okay. The next congestion management is called PQ or priority queuing. Okay, so packets are scheduled strictly based on their priority. Packet in a queue with low priority can be scheduled only after all packet in the high priority has been scheduled. Now let's look into this example. Now notice that the red color is an urgent packet. Okay, so we are going to place them into the high queue. So in the priority queuing, we have 4 queue: high, medium, normal, and low. So we have a second urgent and a non-urgent. Now this is how it actually works. So based on the classification, so the yellow is a non-urgent, the red is urgent, and the second urgent. So the urgent will be scheduled to go out first. Once this is finished, then you go into the second urgent, and finally the non-urgent will be scheduled last to go out. Now this is called a priority queuing. Now this is good because that those urgent packet will go out first. All right. But then again, you will have a bit of an issue because that if let's say you have some non-urgent packet queuing inside here, if let's say you have a high packet that is keep on constantly coming in, I need to schedule this out. Only when this is empty, then it go from high to the medium. And if let's say the medium over here is empty, then only it will go to the normal and finally go to the low. Now assuming that now after the first queue, high queue here is still not empty, I have to finish schedule before I go down here. So there will be a case of those packet that is scheduled in a low priority will have a starvation. In another word, they will be waiting there too long, and end of the day it will become timeout. Even though later you schedule it to go out, it will be useless. So that is on the priority queuing. Now the next congestion management is called CQ. CQ is called custom queuing. Alright, custom queue. So custom queue supports 17 queues. So that is from 0 all the way to 16. In this case, we have 17 queue. Q0 is called system queue. So this one, the system will always go out first. Okay, the packet in other queue are scheduled only after the Q0 are scheduled. So you can see that the schedule here is very similar to the round robin, but in round robin we can't specify the bandwidth. All right, here on each of the queue, after we schedule them into the queue, we can specify individually how much of the bandwidth that we can have on each of the queue, and the queue is actually going through a schedule, all right, through the pooling. So it's very similar to the round robin. Okay, so lastly we have a WFQ. Now WFQ is stand for weighted fair queue. Right, weighted fair queue classify packet into a different type and add classified packet to different queue. You can see that we have a different number of queue over here. So we have a large number of queue here, and the queue are being allocated bandwidth based on their flow weight. So how we can consider the flow weight and how this weight is being considered? Now firstly, you can see that we have the yellow, green and blue that's coming in here. So they are going to classify based on the category. It can be based on the source IP, destination IP, it can be based on your priority, and they will going to do a hashing, and based on the hashing they are going to put them into different type of queue, and each of the queue have their own allocated bandwidth. Okay, and this is being done using the router CPU, using the weighted fair queue algorithm, okay, to differentiate them into different queue, and the queue are actually being sent according to schedule. So weighted fair queue basically is very easy to configure, but the algorithm is fairly complex. After we look into the congestions management, it's time for us to look into congestions avoidance. So let's look into the definition of congestions avoidance. Now it means that the router will actively drop packet when congestions become serious to avoid TCP global synchronization. Now let's have a look over here. Now packet drop basically means that it's subject to tail drop. So if let's say my queue is full, then I have no choice but I have to drop the packet. Now let's look into this graph. Assuming that I have a TCP session and this is my limit, okay, of my bandwidth. So I'm going to start my TCP connection. It's go up, there's no problem, it go up all the way to the top. Now once I hit into the limit and the queue actually full, then the packet will get dropped. Okay, then I'm going to try to slow down, and I'm going to slow start again slowly, and then hit into a limit, and then I come down and slow start again. So what will happen over here is, if I have multiple TCP going on at the same time and I drop at the same time, this is what we call the global synchronization. Now this is the area where there's no packet is actually being sent, or in this case it's not optimized. Now we try to avoid the global synchronization. That is where we have to use what we call the random early detection. Now for us to prevent the global synchronization, what will happen over here is, again, this is my limit. So before it's actually hit to the limit, I'm going to drop, then it's slow start, then it go up, then it's slow start, and I have multiple, so each of these are not hitting to the limit. So in another word, I will have a utilization that is being optimized, that is for RED. So RED is better than the tail drop. Okay, but you notice that over here we are random drop. So when you drop, you can basically drop a high priority packet. Now for us to improve that, now we are going to consider the weight. So we have the weighted random early detection. Now for us to do that, we need to create a drop profile. So under the drop profiles, based on the DSCP that we have, so we have AF21, AF22 and AF23. So AF21 is the low drop probability. Okay, low drop, medium drop and high drop. So you can see that under the high drop, I'm going to drop you once you actually hit on the 25, but I will not drop those that is high priority until that the queue hit into the 35 queue length. Okay, so you have to create a profile, and that is what we call the weighted random early detection. Now all this we have to configure, and the configuration over here is that we are going to configure based on the policy. Now, just now I mentioned that we have the queuing management, queuing avoidance. Okay, then we also have a different method of classification. Now, the traffic policy allow you to do all this. Firstly, we have to classify the packet. Okay, you can classify the packet based on certain rules. The common one will be using ACL. After the classification, then we have to configure the behavior, and the behavior form policy. So we have classification, we classify, then we are going to, based on the classification, it becomes the behavior, and the behavior become the policy. The policy is going to apply to the interface. Okay, so the traffic policy can be inbound or outbound, and you also can implement certain actions such as remarking. So these are the example that I mentioned here: classifier, behavior, and the policy. Classifier is for you to classify the packet. Behavior is to determine that what type of behavior that you want to. Example include filter, which means that you are going to drop them. You can remark them, you can police them, you can ship them, or you can schedule them based on scheduling. It can be round robin, it can be a strict priority or priority queuing, okay, etc. And finally, you are going to implement the policy. It can be based on the interface globally or even to the VLAN. Now let's jump to our ENSP and we have a look on how this traffic policy is being implemented.
Thanks for watching. Please do not forget to subscribe to our channel.